Welcome to Jarnac Tutorial 3, Modeling a Simple Cycle. In this tutorial, you will investigate the basic properties of a simple cycle, and we will introduce the notion of parameter scans. Such cycles are very common in signaling networks, and thus an understanding of their properties is important. We will begin once again by defining our pathway P. We will then declare our species, two floating nodes called S1 and S2. We will continue by defining our reactions. Between S1 and S2, there will be a uni-uni irreversible Michaelis-Menten reaction going in each direction, creating a cyclical arrangement. Initializing our parameters and variables, we set the concentration of S1 and S2 to be 3 concentration units. We will set the Vmax for reaction 1 to 0.1 and the Vmax for reaction 2 to 1. Set both kms to 5. We are now going to use the parameter scan feature to investigate how the activity of the first Vmax affects the steady-state concentrations of S2. To make sure that you've entered everything correctly, compute the steady state with the current values. You should get the following steady-state values for S1 and S2. Once you can reproduce the above values, we can begin to scan the parameter range. The first thing to do is select the particular parameter we wish to scan. In this case, it will be the first Vmax, p.v1_vm. Next, we must set the min, max, and density parameters. Set these to p.v1_vm, 4, and 80 respectively. These indicate where to start the scan, where to finish, and how many values to compute. Next, we will create a matrix which will hold the data we will generate as we change the values of Vmax. The function m equals matrix ij creates a matrix with I rows and j columns. We can access individual cells with the syntax mij. The function setColumnName is useful for labeling our matrix and uses the syntax setColumnName mi columnname, where m is a matrix, I is a column number, and columnname is a string name we wish to assign to the column. We will then create a matrix with scan density number of rows and 3 columns. We will set each column name, the first being Vmax, the second being S1, and the third being S2. After creating the matrix, we will write a for loop which calculates the steady state at each different Vmax value, populating the matrix. We will run our for loop from 1 to scan density, 80, and in each recursion we will perform a short time course simulation to avoid errors in our steady state calculation. Then, we will calculate the steady state, add the new data to the matrix, and increment Vmax. Finally, we will graph this newly created matrix and run the simulation to get the graph that will appear on screen. This graph shows a simple hyperbolic response as the Vmax is increased. Nothing particularly interesting. We will now see the effect of changing the 2 reaction kms on this response. Change both reaction kms from 5 to 2. Now, simply rerun the simulation. The response has changed from a simple hyperbolic to a sigmoid response. Reduce the max value from 4 to 2 in order to rescale the graph, and then decrease the kms further to 0.25. Again, run the simulation to see the effect of the decreased kms. As the kms fall, the sigmoid character becomes more and more pronounced. In fact, it becomes almost switch-like. This property is well known and is called ultrasensitivity. The property enables a network to convert a graded input into an on-off response. This concludes Jarnac Tutorial 3. In Tutorial 4, we will introduce a bistable model and introduce the notion of free format rate laws.